Hi, everybody. So, next chapter, we're dealing with compounds organic compounds that have oxygen, sulfur, and nitrogen in them. And the reason why that's important is because alkenes by themselves are pretty unreactive. They're not involved in a lot of biological reactions, certainly. What you need for reactions to take place are some of these so-called functional groups containing oxygen, sulfur, nitrogen, and other things that allow these organic compounds to undergo important reactions. And we'll learn about some of those compounds and some of the reactions they undergo in this particular chapter. So, as I mentioned, we're going to call these things functional groups because they have a function in having specific chemical reactivities. So they're called functional groups for that very reason. And so elements other than carbon and hydrogen that are present, we call those heteroatoms. And there's lots and lots of different heteroatoms. Basically anything other than carbon and hydrogen. And so organic compounds that have these functional groups in them have similar chemical properties. Like carboxylic acids, we'll talk about those. We've dealt with weak acids. We actually titrated one. Acetic acid, that is a organic acid, and we'll learn about a lot more of them. And the functional group that's involved with being called an acid and why it has those particular functions and why it has those particular chemical characteristics. So most functional groups have the same three atoms in them, as I mentioned before: oxygen, nitrogen, and sulfur. And one of the most common is called a carbonyl group, and that is just a carbon double bonded to an oxygen. We call that a carbonyl group, and that's found in a lot of different functional groups and a lot of organic compounds. And why it's so important is because we know that oxygen has a very high electronegativity, and because of that, it forms dipoles when it's bound to something that's less electronegative than it. And one of those things happens to be carbon. And so we know that is going to form a dipole. And why that's important is because when we have a dipole like that, it actually acts as a magnet of sorts for negatively charged groups or other dipoles, and basically brings electrons towards that carbon and allows, once we have electrons gaining access to that carbon, it can then undergo a lot of different chemical reactions. So one of the functional groups that has this carbonyl in it that we've seen before is acetic acid. That's what we call a carboxylic acid. And the carboxylic acid group is this right here. So we see that it has a carbonyl group, the C double O bond, and it has a hydroxyl group, or an OH, directly next to it. And this group, this hydroxyl group, now has increased negative charge on it because of the presence of the other oxygen. The oxygen withdraws electrons from the carbon and makes this carbon even more positive than it would be otherwise. And because now this carbon is even more positive than it would be otherwise, with a partial positive charge, that makes this oxygen in the hydroxyl group even more partially negative than it would be otherwise, and makes it more reactive. It makes it give this proton away more than it would. An alcohol, which we'll also learn about, also has a hydroxyl group, but it doesn't have that oxygen next to the carbon withdrawing electrons from it. And so it's not nearly as acidic as this particular group. And so that is one of the things that functional groups do, is that they make the carbon around them much, much more reactive and undergo chemical reactions. So the functional group is the reactive part of the molecule. And so a lot of the time we want to focus on the functional group because that's where all the action is going to take place. And the rest of the group we just refer to as R. And why do we call it R? Well, very imaginatively, it stands for the rest of the molecule. So basically, if we have a carboxylic acid group here, we just put R there, and R can be anything, basically. Anything that doesn't have a carboxylic acid group on it. So it can just be a simple methyl group, and that would be acetic acid, or it can be a very long fatty acid chain, and that would be palmitic acid, because it's really, really long fatty acid. So R can represent anything from a single carbon like methyl to 20, 30, 40 carbons, or something like benzene can also be an R group. So here's some of the functional groups we're going to be dealing with. As I mentioned, alkanes really not that reactive. They have just carbon-carbon bonds and carbon-hydrogen bonds, and they're so similar to each other in electronegativity that they don't form dipoles. And so without any dipoles, you don't really have a place for electrons to attack. When, on the other hand, you start to introduce greater electron density that can be moved from one place to another, like with a double bond can be polarized more readily because there's more electrons there. So you can push them towards one carbon or the other. So we get more reactions taking place. And that is indeed a functional group, a carbon-carbon double bond. We know that a carbon-carbon triple bond is called an alkyne. That's also a functional group. The alcohol functional group is this hydroxyl group. And so we end molecules that have that with the suffix OL. OL, all, ethanol, methanol, isopropanol. And then two of the groups we're going to be learning about in this particular chapter called thiols. Thiols, instead of having an oxygen with a hydrogen, it has a sulfur with a hydrogen. And we know that sulfur is bigger than an oxygen. And so sulfur actually is more reactive than oxygen is in these sorts of reactions where electrons are pushed around from one place to another. It has a larger group of electrons. It has a much larger number of electrons, and its electron cloud is larger, and therefore it's more polarizable than oxygen. And so that functional group we call SH4, thiol group. Ethers just have an oxygen between two carbons. So we have a R stands for rest of molecule. So that would be a carbon then covalently attached to an oxygen, and then the other side would also be attached to an oxygen. And so that is called an ether, and we'll talk a little bit more about that a little later as well. Here's some other groups we'll be talking about containing oxygens. We already mentioned carboxylic acids. They have the carbonyl group plus the hydroxyl, which is more active than a typical hydroxyl group. Here we have, you've probably heard of, aldehydes. Aldehydes have the carbonyl group as well, but with a hydrogen next to it. And so the functional group is that carbonyl group plus the hydrogen. and we refer to the suffix there as al. So instead of all for an alcohol, we say al. So methanal, ethanal. So this would be at the end of a molecule. So you have your carbon chain, rest of molecule, and then at the end of it, you would have a functional group for an aldehyde. A ketone also has a carbonyl group, but the difference is there's carbons on one side and there's carbons on the other side. And so that just has a carbonyl group and nothing else. It doesn't have the hydrogen next to it. It has carbons on either side. And we end that with "-one". You've probably heard of acetone. That molecule was in your test last week. So we name those by referring to whatever is the R group on one side of the CO bond and what's on the other side, and then the carboxylic acid. Another one that we'll talk about a little bit is called the esters. Now, if you're going to take organic chemistry a little further, with a lab portion with strictly organic, you're going to make esters in the lab, and it's really fun because esters have this incredible scent to them, and that's formed between a dehydration reaction, and a dehydration reaction means that water is released, and you have a carboxylic acid, and then you react that with an alcohol, and so you release the OH from the carboxylic acid and the proton from the alcohol, and you make this particular bond. So you have a carbonyl group, an oxygen, and then the alcohol. And so you name that by naming the alcohol part first, followed by the acid, like this one. Here we've got methanol reacting with acetic acid. So we would call that methyl ethanoate, or the more common term, methyl acetate, since it comes from acetic acid. And esters are in, like I said, they have this tremendous, wonderful odor to them. You can make them smell like bananas or smell like caramel. And you find them a lot in perfumes and in foods and a lot of other things where like a really, really great smelling substance is required. Esters are really fun. So of the functional groups with nitrogen, there's two basic ones. There's amines, and we're probably familiar with amines. Amines just mean nitrogen bound to hydrogens. And in this instance, bound to hydrogens and a carbon. So a primary amine would be a nitrogen attached to a carbon and then with two hydrogens. A secondary amine would be a nitrogen attached to two carbons and one hydrogen. And then a tertiary amine would be a nitrogen just attached to three different carbons. And there's lots and lots of these types of molecules in nature. So those would be amines. Amides are formed with another dehydration reaction, this time between a carboxylic acid and an amine. So we get this bond. We get our carbonyl. Like I said, carbonyl is really, we find that over and over and over again. And this time the carbonyl is attached to an amine group. And so we name the acid first, the carboxylic acid first, and then we followed by whatever the name of the amine was. And then we call that amide. Like here, we have a phenol group, or basically a benzene ring with a carboxylic acid, and an amine, and we call that benzamide because it comes from benzene and it has an amine on the end. So the amide just refers to the carbonyl group followed by an amine. So we'll deal with some of these during the lecture tomorrow. So alcohols. You're probably familiar with alcohol. We talked a little bit about them. Basically, all it is just a group of carbons that has a hydroxyl group attached. And it either is attached to the end of a molecule or it can be basically placed anywhere. And when we name it, we would just have to say where the hydroxyl group or the alcohol group is. That's what we call the alcohol substituent group, a hydroxyl group. And we just use the ending OL to indicate that it's a chain of carbons with an alcohol group somewhere in them. And then in the name, we would give the number to say which carbon has the alcohol group or the hydroxyl group attached to it. Now, alcohols can hydrogen bond because they've got an oxygen directly attached to a hydrogen, just like water does. And so they can hydrogen bond with each other. And because of that, they have a much higher boiling point than typical organic compounds that are similar to them. Like for instance, if you look at methane, methane has a very, very low boiling point, minus 164 degrees. All you need to do to increase that tremendously is just pop off one of those hydrogens and replace it with a hydroxyl group. And it goes from minus 164 to plus 65. That's a huge difference. And the only difference between them is that one of them can hydrogen bond and the other one can't. They're practically the same size. And then that boiling point will increase the longer and longer the side chain gets. Because not only can you hydrogen bond now, you can also do greater and greater London dispersion forces. So ethanol boils at a higher temperature, propanol boils at a higher temperature, and so on and so on and so forth. But it's the hydrogen bonding that really does most of the heavy lifting there and increases that boiling point tremendously. Some of the common alcohols, no doubt you've heard of, methanol and ethanol. Those are really, really common solvents in the lab. We've got propanol, 2-propanol, also called isopropyl, because when we have a carbon on either side and then something attached to the middle carbon, we basically say that that's not quite a propyl group, it's an isomer of a propyl group, and so we call it isopropyl. And everyone should recognize what this one is, because we basically were naming those in our last test, cyclohexanol. And we don't have to give a number when we're dealing with a ring structure, because wherever the substituent is, that's assumed to be carbon 1. So cyclohexanol, we would say the hydroxyl group is at carbon 1. So a primary alcohol is at the alcohol group, the hydroxyl group is at the terminal end of the molecule. Secondary is when it's bound to an internal carbon. And then when you have something like this, basically that alcohol group is attached to a carbon that has nothing but carbons attached to it. And we call that a tertiary alcohol. Not a lot of those, but they do form. And so sort of a nickname for them, we call it TERT for tertiary. But the real name for this would be 2-methyl-2-propanol. Okay. So let's look at some reactions alcohols undergo. So one reaction that actually produces alcohols is taking a carbonyl group and then reacting it with hydrogen. So here we have a very special carbonyl group that's a triple bond in carbon monoxide between carbon and oxygen. So under very high pressure with hydrogen, this gets reduced and we form, that carbon goes from being triply bonded to oxygen to being singly bonded to oxygen, and the oxygen also gets reduced. It gets added, hydrogen gets added to it. So now basically we replace all those bonds with hydrogens except the carbon-oxygen bond. And so we go from carbon monoxide to methanol. Other reactions that can take place is that here we have a ketone. I have a carbon group on one side of a carbonyl, and I've got a carbon group on the other side of the carbonyl. Again, under huge pressure, high temperature, we add hydrogens to this. And so we break one of the double bonds, one bond of the double bond, and we put a hydrogen on that oxygen. This would form a secondary alcohol. Okay? This one you should already know because we've dealt with this before. This is the Markovnikov reaction, where we basically hydrate a double bond. So here we've got an alkene, and then with a catalyst of a very strong acid, usually sulfuric acid, we basically force that double bond to break and then take on water. And when it takes on the water, remember, the carbon that has more carbon-carbon bonds gets the hydroxyl group, and the other one gets the hydrogen. That makes an alcohol. Alcohols could also get oxidized. Basically, they can have electrons taken from them. And so under those circumstances, here we have a primary alcohol, meaning we've got the hydroxyl group at the end of the carbon chain, high concentration of oxygen, the reaction goes forward, and this gets oxidized to an aldehyde. So basically this proton gets pulled off, and that oxygen then gets double bonded to the hydrogen. Basically, it's the same reaction in reverse that we talked about before. When you add hydrogen, you break the bonds and add the hydrogen. When you oxidize, you're doing the opposite. You're taking electrons away. And where there was single bonds before, you'll be left with double bonds, and that hydrogen will be gone. And if we keep oxidizing that aldehyde, we actually add another oxygen and go from an aldehyde to a carboxylic acid. So we go from an alcohol first at the end, and then we form an aldehyde by removing the hydrogen from the oxygen and forming a double bond. And then we oxidize it even more by removing that hydrogen and replacing it with a hydroxyl group and make a carboxylic acid. Now, when you have a secondary alcohol, so the OH group is no longer at the end of the molecule, we have a secondary, and we oxidize that, we get the same reaction where the hydrogen leaves, and then those electrons then get shared with the carbon in a double bond. But instead of an aldehyde this time, we get a ketone. Why? Because the alcohol group is not at the end of the carbon chain. It's in the middle somewhere. And so we can't form an aldehyde because an aldehyde has to have this format. A ketone would have our carbonyl group with carbons on one side and carbons on the other. That's a ketone. And then when we oxidize the ketone, nothing happens, because basically we don't have another hydrogen there to pull off and take away. This carbon with the double bond has no hydrogens. It's double bonded to a carbon on that side, double bonded to the oxygen, and it's single bonded to a carbon on each side. So there's no hydrogens to remove. So you don't get a reaction when you have a ketone. And then when you have a tertiary alcohol, you don't get any reaction at all, because just like with the ketone, this carbon that's attached to the hydroxyl group has 4 bonds already, and none of them are with a hydrogen. So there's no hydrogen to remove. And since it already has 4 bonds, you can't make it bond to anybody else. And so there's no reaction when you try and oxidize a tertiary alcohol. Now this has a really important function in biology, especially if you've been hitting it kind of hard over the weekend. So we know when we drink ethanol, we know the effects of ethanol, and then that ethanol gets broken down by an enzyme in your body called alcohol dehydrogenase. And what do you think a dehydrogenase does? It removes hydrogen. That's what it does. So basically it oxidizes alcohols. It oxidizes the alcohol and removes that hydrogen, forming an aldehyde. And the aldehyde it forms is ethanal, also known as acetaldehyde. And that is what gives you the really bad hangover, because this is a very reactive molecule and undergoes a whole lot of reactions that your body does not appreciate. And so, yeah, aldehydes are very reactive molecules because they have that hydrogen that's right there ready to leave. And so it forms all sorts of compounds. It finally starts calming down when all that ethanol gets oxidized even further to a carboxylic acid. Carboxylic acids aren't nearly as reactive as aldehydes are. And so once you've converted it to acetic acid, you start feeling a little bit better, but you wish it would happen a lot faster. So you can also dehydrate alcohols, just like the Markovnikov reaction where we actually add water to a double bond. We can make that reaction go in reverse by adding very strong acid and heat. And in those circumstances, we take an alcohol, and the strong acid actually pulls off the hydroxyl group and forms that double bond again. So that would be our product, and then water is the other product. So when we want it, basically very, very strong acids will oxidize things. And so we can reverse our hydration reaction by doing a dehydration reaction. And it would just be the Markovnikov reaction going in the opposite direction. And we'll name these tomorrow as well. So ethers can't hydrogen bond because they have carbon group on one side and a carbon group on the other side, and they have an oxygen, which could be a hydrogen bond acceptor, but there's no hydrogen bond donor. So an ether could hydrogen bond with water, for instance, because water is a hydrogen bond donor. It could hydrogen bond with that hydrogen there, but ethers can't hydrogen bond with each other. They do have a dipole, not a particularly strong dipole, but they do have a dipole. So they will have a higher boiling point than other molecules. For instance, here we got propane. We take out the methyl group, or the methylene group, CH2 group, we also call that methylene, in the middle, and replace it with an oxygen. You can see the boiling point increases somewhat, but not nearly as much as if we added the ability to hydrogen bond by putting a hydroxyl group there. So they have slightly higher boiling points than similar sized molecules, but not nearly as much as alcohols do. So when we name ethers, we basically we have the oxygen in the middle, and we basically name the two groups on either side. Whichever is the longer one, we name that one first. So in this instance, we have an ethyl group on this side and we have an ethyl group on that side. We would just call it diethyl ether. If we had an ethyl group on one side and a methyl group on the other side, we would call it ethyl methyl ether. So the ether that most people are familiar with is diethyl ether. That was the first one that was used in the operating room as an anesthetic, and it basically knocked people out. Basically, it gets you super drunk because it basically looks like it looks like ethanol, but it has a much higher, much lower boiling point, and so it's basically a gas, much higher vapor pressure. So you just breathe it in, and basically knocks you out. So you generally don't feel great. We don't use it as an anesthetic anymore, but you basically wouldn't feel great after coming out of that one. So let's look at aldehydes and ketones. So those have carbonyl groups in them, where ethers don't. So why carbonyls are so much more reactive and so much more polar, is because they have this big separation in charge. They have the carbon-oxygen double bond. And when carbon's sharing more electrons with oxygen, oxygen pulls even more of those electrons away from the carbon. When carbon's only sharing one pair of electrons with an oxygen, it's basically only losing 2 electrons, or moving a little closer. But when it's sharing 4 electrons with oxygen, it's losing 4 electrons. So those electrons are spending more distance away from the carbon. So you get an even greater imbalance in charge. The carbon has a higher partial positive charge, and the oxygen is a higher partial negative charge. So it's a much greater polarity. So when you have an alkane, when all you have is LDF, London dispersion force, you get a fairly low boiling point. So like I said, you take one of those methylene groups out, replace it with an oxygen. Now you have a weak dipole, and the boiling point goes up a little bit. When you add an aldehyde group, now we have a strong dipole on the end of that molecule. The boiling point goes up even more. And then when you have an alcohol, where you have oxygen covalently linked to a hydrogen, now you have hydrogen bonding, and the boiling point goes up even further. So aldehydes and ketones give you that very strong dipole, and also allow a lot more reactions to take place because of this big difference in charge. This acts as a very convenient place for electron-rich groups to attack that carbon and then undergo reactions. We're not going to get into a lot of that. That's more sort of advanced organic chemistry. But the reason, I just sort of want to point out, the reason why it's more reactive is because you've got that big separation in charge, and it basically gives you a spot where reactions can take place, particularly with groups that have high number of electrons that can be easily polarized. So when you name these things, a lot of stuff here. We'll sort of go over it briefly. When you're naming aldehydes and ketones, basically, just like we did before when dealing with alkanes and alkenes, find the longest chain of continuous carbons. That's going to be the parent alkane or alkene, whatever the group of carbons is. Whatever is the longest one, that's where we start naming it. And then if it's an aldehyde, you drop the E from the alkane name, so it's not methane, it would be methane al. Or it wouldn't be ethane, it would be ethane al. And remember, an aldehyde is always at the end of the molecule because we have carbon, 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 and then the double bond, and then the hydrogen. So that carbon can't be attached to another carbon. It's got two bonds with oxygen, one with hydrogen, and the other one to the carbon chain. It can't be bound to anything else. And so that is always at the terminal end of a molecule for aldehydes. So those are pretty easy to name. You don't even have to give a number because we all know it's going to be at the end of the molecule. For a ketone, it's a little trickier. We drop the E and add -one. So instead of propanone or butanone or something, basically how many carbons are in the base or in the chain. If it's butanone, it would have 4. And then we would also have to give the number, because in this instance, if it's got more than 3 carbons, we don't know which, or actually more than 4. We don't know which carbon the carbonyl is on. If it's got 3, we know it's on carbon number 2 because it has to be on an internal carbon. If it's got 4, it has to be on carbon 2 because we go in one direction, it's going to be on 2. If we go in the other direction, it's going to be on 2. So to indicate the substituent on a ketone, we always want to give the carbonyl carbon the lowest possible number. So if you have an 8 chain and it's on the 3rd one, you would call it 3-octanone rather than 5-octanone because 3 is a smaller number. And in cyclic ketones, just like with other cyclic alkenes we talked about, wherever the double bond is, remember on a circular alkene, that's carbon 1. Same thing is true if you have a circular alkane and a carbonyl on it. We just assume that the carbonyl that's carbon 1, and then every other substituent you would name from there. So again, aldehydes, pretty straightforward. There's a lot of common names for aldehydes because we've just been using them for so long. These are the new names. The IUPAC names are the new names, but the other ones are common names are the ones that have been used for hundreds of years. Like you've no doubt heard of formaldehyde. Formaldehyde is used to basically preserve things. And the reason why it's used to preserve things is because it's super, super reactive. And it basically cross-links anything with carbons in them. So it basically takes 2 carbons and connects them. 2 carbons from anywhere, connects them. So it's used as a cross-linker. And so it basically keeps things from falling apart. So methanal, ethanal, propanal, butanal. Just find whatever the long chain is, name it, put al at the end. I won't ask you to memorize formaldehyde and acetaldehyde and anything. Formaldehyde you probably are familiar with. Formaldehyde, probably should know that one. And it's the simplest aldehyde there is. You can't get a smaller one. It's basically the carbonyl group with 2 hydrogens. That's it. Naming ketones, our suffix is then -one. So propanone, that would have 1, 2, 3 carbons. And since it's a ketone, it's got to be an internal carbon, got to be the one in the middle. So We would call that propanone. Butanone, we could also call that ethyl methyl ketone. And to be honest, I don't know why they would put the 2 there, because obviously it's on carbon 2. That's the only place it could be. I guess you would put it there. You would put the name in there if there were other substituents. But just calling it butanone, I think, would be fine. Pentanone, since there's 1, 2, 3, 4, 5 carbons, you definitely need to give the number there, because it's either carbon 2, this being carbon 2, or that being carbon 2. If it's in the middle, that would be carbon 3. So you would call it 3-pentanone. So here we have 6 carbons, and we would give the number the smallest number possible. So it's at, instead of being at carbon 5, we say it's at carbon 2, and just call it 2-hexanone. And when you have a circular alkyl chain, circular alkane, remember, we don't have to give the number at all, because this is assumed to be carbon 1 right there, because it has only one constituent. It's the ketone, and so basically we just call it cyclohexanone. We'll name these during the lecture. Now, for the end, let's talk about mercaptans a little bit. Mercaptan is this group. That's a thiol. And so a mercaptan is a molecule that has a thiol group, and they reek. I mean, we're all sort of familiar with that sort of rotten egg smell. This is actually added to natural gas. So if you have a natural gas leak in your house, you will smell this. This is hydrogen sulfide. And so it's basically added to it to let you know it's there. Because if it wasn't there, you can't really smell propane. It doesn't have an odor. And so your whole house would fill up with it, and you would like suffocate, and you'd have no idea. So hydrogen sulfide is added to it to sort of let you know that like something bad is happening. Deal with it. Probably familiar with this one too. There's a lot of skunks around. We went driving up in the mountains this weekend, and man, it was like a skunk apocalypse up there. Skunks everywhere. Poor things by the side of the road. So it's 3-methyl. So 1, 2, 3 methyl group. So it's got 4 carbons all together. So butane, and then thiol, because it's got the old thiol group on it. That's the skunk odor. And then if anyone's had a skunky beer, haven't had one of those in quite a while, the skunky beer smell is the very same molecule that skunks give us, but there's a double bond there. And so that would be 3-methyl 2-butene 1-thiol. So we give a number for the thiol because that could be anywhere. It could be on the end, it could be in the middle, it could be pretty much on any of the carbons. So we have to say where it is when we're dealing with mercaptans. So there's a lot of similarities between oxygen and sulfur. We know that chemically they're very similar, but they do have some differences. So when we're naming them, so if it's on the end of a molecule, it's an alcohol, and the group is called a hydroxy. Now that's, instead of oxygen, it's a sulfur. We say it's a thiol, and that's a mercapto group. So that's terminal. Now if it's in the middle, that's an ether. And we call substituent on either side alkoxy. And I'm not going to deal a whole lot with that, but like you could, it's another way of naming them. Like this, we would call a methoxy group. And that makes sense, right? Because it has a methane, a methyl group, and an oxygen. So methoxy. If that we add another carbon, make that CH2, put another carbon there, that would be ethoxy. And the same is true for the sulfur. Instead of an ether, we would call that a sulfide. So diethyl sulfide, dimethyl sulfide. And we would call each of those an alkythiol. That would be the substituent. Now, the main difference between the oxygens and the sulfur is that since sulfur has a larger electron cloud that's more easily polarizable, it's a little more active than oxygen. So if you have this group at the end, it's a lot more acidic than alcohols are. Alcohols almost never deprotonate. You almost never get a hydrogen being pulled off of an alcohol, unless under extremely harsh conditions like very high acid and temperature. Thiols, on the other hand, are much more acidic and tend to lose that proton much more easily. And we call this a thiolate, which is a really weak base. And so that pretty much stays negatively charged. This is an excellent nucleophile. What does that mean? A nucleophile is something that's basically negatively charged and will send its electrons to another group. And what's the group it normally sends its electrons to? Carbonyl. So that's why you have this attack, we call it a nucleophilic attack, at the carbon. We have a negatively charged molecule that likes to spread its electrons around. Sulfur has a large electron cloud. And we have this carbon with a larger partial positive charge than usual. So it makes it very reactive. So these are like sort of a little more advanced reactions, but basically we want to firm in on the fact that what these mercaptans can do and the sort of reactions they catalyze. One of the most important biologically is when it's oxidized. So if I have two different thiol groups, what will happen is that each of them will lose the hydrogen and form a disulfide bond. And this happens a lot in biology. There's a lot of proteins that are kept together by these disulfide bonds. Think of them basically like magnets. So if you have like a big protein with lots of amino acids, floating around in space, and it's like kind of floppy, you don't want it to flop around, because when it's flopping around, it can't catalyze its reactions. It needs to stay in a very particular three-dimensional shape. Well, how does it do that? A lot of proteins form these disulfide bonds, which basically lock the protein in place. And that's due to an amino acid called cysteine. Cysteine is a thiol. It has a mercaptan group on the end. And it's when two cysteines come together and are oxidized, they form the disulfide bond, and that keeps them together. And then us in the lab, when we want to study a protein, we want to break it apart, one of the things we will add is another thiol to reduce these bonds and break them apart. That way we can break the protein apart and get in there and clip it up into pieces and do whatever reactions we want. So another thing I want to point out is that with all these functional groups we've been discussing, you're going to find them on amino acids, because it's the amino acids in proteins that do all of these reactions. So all these enzymes that do all these biological reactions for us have to have these functional groups in order to catalyze the reactions. So you can see amino acids that have positive charges on them. Arginine has a permanent positive charge, and it also has these amines attached. Lysine has an amine at the end. Negative charges, acids, carboxylic acid. We have two of them. We have aspartic acid and we have glutamic acid. Glutamic acid is slightly longer. If you want uncharged, but you need some sort of reaction, we've got serine with a hydroxy group. We've got threonine with a secondary alcohol. We have asparagine that has an amide bond. We have glutamine that has an amide bond. And then we have cysteine that is a thiol. So all of these functional groups you're going to find on amino acids, because it's amino acids that have to catalyze these reactions. So that's it for now. We'll talk more about this tomorrow, and read the chapter. There's a lot in there, and we'll go over a lot of this and do the recitation, which I will be posting this evening. All right, talk to you soon.